Okay, so we're going to take a look at equilibrium calculations. These are a lot of fun. These are fun is a relative term I recognize, but these allow us to kind of solve this like a puzzle. So let's take a look at this first one. So the first one is pretty simple. It's determining Kc from a known equilibrium concentration. Okay, so we're going to determine Kc from a known equilibrium. So here we go. For the reaction of A goes to B. Whenever we have an equilibrium problem, one of the first things I want you to do is I want you to write out the equilibrium reaction, as well as the equilibrium expression. Kc is equal to the concentration of products over the concentration of reactants. There it is. Okay. So now once we have this, now let's read through. The equilibrium concentrations are, well, we have this, which is at equilibrium. And we have concentration of B also at equilibrium. So actually life is super easy right now. We know that we have these concentrations. The concentration of B is 0.0100 molar. Concentration of A is 0.200 molar. And so we can just solve for Kc simply by plugging those values in. So again, this is as easy as it gets. This is as easy as it gets because we have, we already are given the equilibrium. Most of the time, you're not going to be given the equilibrium values. You're going to have to solve for them, or you're going to have to figure them out in some sort of way. And we're going to walk through that as well. But this is the simplest version of the problem. So from known equilibrium concentrations, 0.01 divided by 0.2 gives me 0.0500 molar. Oh, not molar, sorry. There is no unit. This should be unitless. And that's what we get. There's our answer. Our Kc is equal to 0.0500 molar, or 0.0500. That's it. That's my Kc. Fantastic. So your charge is to do this. New reaction, write the Kc, substitute those values in, and solve for the value of Kc. Next up, we are missing the equilibrium concentrations, so we need to do a little bit of work. I've already written out the equilibrium reaction for you, so we're just going to use that, and we're going to continue on. So again, I'm going to write out my equilibrium expression, concentration of products, HI, which is going to be squared. Of course, it's squared because the coefficient in front, times over concentration of H2 times concentration of I2. There we go. There is my Kc for this reaction right here. So before I said I want you writing out the equilibrium reaction as well as the equilibrium expression being the Kc. And we're going to take it one step further. I also want you to create a table. So I wanted you to take your reaction, whether you wrote it down or it was provided for you. And I want you to create this small table. Actually, it's this. Here we go. All right. So all of the values in this are going to be in molarity. And we're going to do the initial value, the change that's occurring, and ultimately we're going to end up with equilibrium as well. We're going to call this an ICE table, initial, change, equilibrium. It's just a shorthand for it. I'm just usually going to put ICE for initial change and equilibrium, but I wanted to show you where that came from. From that, I want to make sure that you recognize that we are not going to care well, we only want the equilibrium value. So I'm going to kind of add another line here because it's going to be the difference of those two that's going to give us the value at equilibrium. So now we're ready to go. So this is how you should prepare. Unless it's a really simple problem, this is how you should prepare every single one of these problems. So let me pause for just 1 second. Okay, it's quieted down. So this is how we start the problem. And now let's just walk through the problem and let's read what we've got. Again, we established we've got the equation with our ice table, and we've got our equilibrium expression. So in a closed system, okay, initially containing 1 times 10 to the 3 H2, 2 times 10 to the 3, 2 times 10 to the 3 I2, so 1,000 molar H2, and now we're just going to plug this in. So initially I have 1,000 molar of that, 2,000 molar of I2, fine, fantastic. Oh, in fact, I just noticed a problem. This is solid. We're going to call this gas for the time being. Cannot be solid. We're not allowed to have that in the equilibrium expression. All right, so there we go. At 448 degrees Celsius, a lot of the time temperature doesn't become involved, but we usually mention temperature. But so I'm just going to ignore that for a second. Analysis of the equilibrium mixture shows that the concentration of HI, so equilibrium mixture shows HI is 1.87 times 10 to the negative 3, or 10 to the 3. So that gives me at equilibrium, I have 1.87, or I guess 1870. 1870 for HI. Calculate Kc at this temperature. Okay, so here is what we're going to do. What we really need to find are these values right down here. I want to know what the equilibrium values are, because if I'm looking for Kc and I know the equilibrium values, then we're good to go. If we know those, then we can plug those in and we can solve our problem. And we have all the information that we need. So this is somewhat like a Sudoku puzzle in a way. How much, is there anything else that I can fill out? How much HI do I start with initially? Was there any mention of any HI? No, there wasn't. So we can assume that we start with 0 HI initially. Okay, so we have no HI initial. Now, once we look at this again, we can see, well, if we start with 0 HI and we end up with 1870, we know that the change is a plus 1870. That's how much we ended up with. I want to kind of look at this in a different way. So we gained that much. Okay. The way that this reaction is working is every H2 that reacts gives me 2 HI. Every I2 that reacts gives me 2 HI. So another way that we can think about this, and we're going to have to think about this in the future, is I am losing minus X amount of H2 minus X amount of I2, giving me plus 2X amount of HI, right? So for every one hydrogen I lose, I gain twice as much HI. For every one iodine I lose, I gain twice as much HI. So if I have gained 1870 HI, what I've done is I've actually only lost half as much. That's twice as much as X. So that means that X is going to be negative 935. Negative 935. Does everyone understand where I'm getting those numbers? I hope you do. Again, if this goes up 1870, so I have 1870 at the equilibrium. For every one of these, I gain 2 of these. So if I've gained 1870 of this, that means I've lost half as much of that. So ultimately, now we're just going to do the math. 1,000 minus 935 gives me a value of, I'll actually write that out. 1,000 minus 935 gives me a value of 65 at equilibrium. 2,000 minus 935 gives me a value of 1,065 at equilibrium. So there we go. We have our equilibrium numbers, and life is simple at this point. I can plug those values in. So once you have the equilibrium values, now we can plug those concentrations in. We're gonna plug them into the equation that we have. So that's HI, which is 1870 squared, times H2, which is 65, times I2, which is 1,650 or 1,065. All right, we just, 1,065, and we do the math. and you end up with, oh, sorry, you end up with 50.5. There we go. We have our final answer. We have our equilibrium of 50.5. That makes sense? I hope so. Reactant or product favored. This is product favored. Does that make sense? Yeah, that number is much larger than those two. This is in fact product favored. Good, that was it. I don't need all this extra space, but that's the idea. Good, so those are the types of problems you're gonna run into where you're missing equilibrium concentrations. You kind of have to find it, discover it through creating that ICE table. Once you've filled this out, then you can move on to this problem. All right, good. Next, the next type of problem that you're gonna have is determining equilibrium concentration, determining equilibrium concentration. So this time we're actually going to be provided a value of Kc, but I want to know how much stuff I have at equilibrium. And let me just add, before we continue with this problem, let me just say that you're always going to solve for these ICE table terms, and they're going to be kind of hidden sometimes. Like when we get to acids and bases, we're going to talk about pH. Well, pH represents the amount of H plus at equilibrium, right? So a lot of this stuff may seem hidden, but you get used to it when you're a chemist. You get used to calculating these. So determining equilibrium concentration. So now we're given Kc, and we have to solve for the values of those at equilibrium. So those are what we're looking for, okay? So with that said, nothing changes though. What are we trying to, what do we always do? Kc is equal to the concentration of products over the concentration of reactants. Okay, and we are going to create our ICE table. Okay, and now we're going to solve, we're going to plug in numbers. So for the following value, okay, so we do know Kc. Kc is 3.2 times, actually, I'm just going to do it down here. Let me rewrite this. 3.2 times 10 to the negative 34 equals concentration of H2, concentration of Cl2, concentration of HCl squared. All right, good. Okay, so how do we proceed? Well, let's find out what we need. So if the initial concentration of HCl is equal to 5 molar. So I have the initial concentration of HCl is 5 molar. Was there any mention of H2 or Cl2? No, there wasn't. So we can assume we start with 0 of that. You can usually assume if you have all of reactant, some reactant, you have no product. So most of the time we have no product. So there we go. Now we have no other numbers to insert, but we can still finish this table. So instead of saying, all right, I've got values because we have an equilibrium number, we don't have an equilibrium number. So now we have to use a variable. So what we can say is I have lost 2x amount of that. And the 2 is going to be from the 2 is from the coefficient. So what I've lost, for every 2 HCl I lose, I gain positive X amount of H2 and Cl2. Does that make sense? Great. So there we go. We're all set there. And so let's complete this idea. Let's combine those two terms. And you don't have to have an answer here, and you're going to see why in a second. 5 minus 2x, that right there is my equilibrium concentration. 5 minus 2x. My equilibrium concentration, 0 plus x, is just simply x, and then 0 plus x is just simply x. So I now have my equilibrium concentrations for my products as well. So now let's solve it, because now I have 3.2 times 10 to the negative 34 is equal to x times x all over 5 minus 2x squared. Okay, is there anything that I can do here? Well, x over x is going to give me x squared. And we can do a couple of mathematical tricks here, and we're going to see that there are a lot of math tricks that we can do. Well, both the top and the bottom, so focusing on this, so we need to solve for x. Both of these are squared. So if I actually take the, in fact, I'll just get rid of this so we can see it easier. If we take the square root of both sides, what you end up with is the square root of 3.2 times 10 to the negative 34. That's an actual answer, 1.78 times 10 to the negative 17 is equal to x all over 5 minus 2x. I've just basically gotten rid of the square. Okay, and now what? Yeah, so we're simply going to cross multiply. So 1.78, and I'm going to do this the slow way, 1.78 times 5 minus 2x is equal to x. So I'm going to distribute that 1.78 through. You end up with 8.9 times 10 to the negative 17 minus 3.6 times 10 to the negative 17. X is equal to x. And now I'm simply going to add the x term to both sides, right? Negative 17x to both sides, 3.6 times 10 to the negative 17x. And that's a very, very, very small number. So what you end up with is ultimately x is equal to 8.9 times 10 to the negative 17. Maybe this is not a great example to do just because the numbers are going to, but either way, that's totally going to work. So x is equal to 8.9 times 10 to the negative 17, but we're not finished yet. Okay, so the last little bit of this is we have to recognize that, okay, well, the concentration of H2 is equal to the concentration of Cl2, right? Which is equal to x, and we know that x is equal to 8.9 times 10 to the negative 17 molar, because it is molar. But that also means the concentration of HI, which is equal to 5.00 minus 2x, is equal to 5.00 minus 2 times our x value of 8.9 times 10 to the negative 17. The concentration of HI, that's going to go away because that's a tiny number, is essentially 5 anyway. There we go. So that is the actual answer. That's the thing that we would be interested in. 5 molar, I should say, is the concentration of HI. And there's the answer for my Cl2. Good. Okay, so this one might be a little bit easier to find, or so yeah, so let's see. So in that one, we were given Kc, we're solving for equilibrium expression. Next up, same exact concept, but instead of being given, we're not given as much. So let's solve this problem. What's the first thing that we do? Again, we write out the equilibrium reaction. A as a gas plus B as a gas is in equilibrium with C as a gas. My Kc is equal to the concentration of products, C, over the concentration of A times concentration of B. Good. And now we're going to create our ice table. Molarity, initial change, equilibrium. There we go. And what do we have for values? So let's take a look. 2 times 10 to the negative 2 moles of A, 3 times 10 to the negative 2 moles of B are placed in a 2-liter container. All right. 2-liter container, this many moles, and we're looking for molarity, yeah? So what we really need to recognize is the concentration of these things is, right? So the concentration of A initial is equal to I'll just move the decimal, 0.020 moles, I should say, per 2 liters, which is actually coming out to be 0.010 molar. Okay, so essentially we're just going to have it because we're just recognize that it needs to be in molarity. And so if you have units that are not in molarity, you got to make sure that they come in molarity. So concentration of A was 0.01 molar. Concentration of B is 0.015 molar. Okay, place a Cthulhu. And if the equilibrium concentration of C is 4 times 10 to the -3 molar, so notice this one does come in molarity, weirdly enough. So this one is 0.004 molar. Let's solve for Kc. So again, we have to think about what these values need to be. I know that we have 0 initial C, right? And because it's a 1-to-1 ratio, we can assume that we are gaining 0.004 C. We are also losing 0.004 B and minus 0.004 A. And now we just simply focus in and do the math. 0.01 minus 0.004, let me just write that down, 0.01 minus 0.004 gives me a value of 0.006. Same thing for the other one, 0.015 minus 0.004 equals 0.011. And there we go. We have our equilibrium values and we just plug them in. So Kc is equal to concentration, so 0.004 molar, divided by 0.006 molar times 0.011 molar. So Kc is equal to 60.6. Reactant or product favored. Product favored, does that show? Not much, actually, but yes, it is product favored compared to how much we started with. It is in fact product favored, but the ratio is correct. Good. Okay. So that is it. So you should be able to calculate the rest of these. Let me see. Yeah. We are going to run into a problem here. I'm going to have a handful of problems for you guys to do in class. So you can give this one, I would give this one a go right here. You should be able to figure this one out. I do want to record this one here. So let's just write this one out. These are annoying, but they do exist. So here we go. This is as annoying as they actually get. So again, for this reaction, I would give this a go. Yeah, I would pause this and give this a try and see what you run into. And here, I'm going to do it now. Again, you should start with COCl2 gas is in equilibrium with CO gas plus Cl2 gas. Again, we're going to make this ice table. There's my ice table. We're going to write out my equilibrium expression. Kc is equal to the concentration of CO, concentration of Cl2, concentration of COCl2. There we go. Got everything we need. Let's actually plug in values. So the value of Kc is 2 times 10 to the minus 10. Okay, we can do that. 2.2 times 10 to the minus 10. And now we need to plug in the values of equilibrium that we have. All right, do we have anything other information? The initial concentration of COCl2 is 2 molar. What are the concentrations of these at equilibrium? And we can do that. So I know that the initial concentration of COCl2 is 2. Well, we know that there was no mention of either of these, so we have 0 to start, and we have no equilibrium value. So now we just have to say, well, we're going to lose X amount of this, and we are going to gain X amount of each of those. Meaning we have 2 minus X, X, and X. These are our equilibrium values. So X times X on top is going to be X squared over 2, I'm just going to say 2 minus X on the bottom. Let's cross multiply. So, so this is the problem we run into. I can't do that little square root trick here because I'm going to take essentially the square root and both things are not squared. And this is where the problem comes in. So what do we do in this situation? So we have this. What do we do? Well, let's cross multiply and let's see. So what we end up with is X squared is equal to, and then we're going to, well, I guess I'll write it out. 2.2 times 10 to the negative 10 times 2 minus X. So X squared is equal to 4.4 times 10 to the negative 10 minus 2.2 times 10 to the negative 10x. Anyone recognizing this? Yes, recognizing this yet? Okay, so now that we have this, what do we do? Let's just put everything on one side. X squared plus 2.2 times 10 to the negative 10x minus 4.4 times 10 to the negative 10 is equal to 0. Yeah, you guessed it. We are going to do the quadratic. So my A is equal to 1. My B is equal to positive 2.2 times 10 to the negative 10. My C is equal to negative 4.4 times 10 to the negative 10. And so now with that, we can use the quadratic equation. Hopefully you remember the quadratic equation. X is equal to minus B plus or minus square root B squared minus 4AC all over 2A. Okay, and so now we solve for it. I hope you know how to do this. We're basically just substituting these numbers in. I'm going to copy these. We're substituting these in for their specific types. So there's A going in for A. There's B going in for B. And C going in for C. Oh, there's an A down here as well. And you're going to plug those in and you get two values. X equals 2.1 times 10 to the negative 5. Or X is equal to, because X can only have one value here, negative 2.1 times 10 to the minus 5. Can we throw any of these out, or can we choose one as being correct? And we absolutely can. This is correct. This one would get tossed out because we can't have a negative concentration. So that makes sense that that's going to be our X. So now that that's our X, we can say, well, the concentration of COCl2 is equal to 2 minus X, which is equal to 2 minus 2.1 times 10 to the minus 5, which is essentially equal to 2 anyway. So equals to 2.00 molar. So there's the concentration of my COCl2, and the concentration of CO, which is equal to the concentration of Cl2, is equal to 2.1 times 10 to the negative 5 molar. There we go. That's the second answer. Oof. Yeah, it's brutal. We want to avoid this at all costs. And so you can always do the quadratic, but there are a couple of shortcuts that we're going to use. They're going to help us avoid the quadratic equation. All right, good questions? All right, sorry this is taking me so long. It's an important topic. I'm actually going to talk about, I'm just going to create one more quick video. It's just this page. Actually, no, I'll just do it here. So applications of the equilibrium constant. So the equilibrium constant K gives you this idea of ratios that will exist. Nature will tell you that this is what it needs to be. The reaction quotient is this neat idea of things when they are not at equilibrium. So Q is the same exact thing as K, only not at equilibrium. Not at equilibrium, and we have a Q value. So to calculate Q, we're essentially looking at the equilibrium expression. We're looking at the same exact thing. So if we look at our generic reaction of AA equals BB equals CC, notice that my KC and my Q are the same exact thing. The only difference is Q can be used, we can use these concentrations at any point, right? It's not specifically at equilibrium. So as an example, the way that we really use this is, let's just say our K is equal to 5. Okay, let's just say that that is our ratio. So what that means is if K is equal to 5, and we have all reactants. So we have 100% of reactants of whatever we've got. My Q is equal to the concentration of products over the concentration of reactants, right? Well, if we have all reactants, essentially I have 0 products and 100% reactants, right? So Q is equal to 0 at that point. Essentially, I don't really need to do equals. It's around 0 at that point. It should be exactly 0, but it's around 0 at that point. So what Q is telling us is, in this moment, in order to reach equilibrium, Q has to increase, right? So if we're in this situation right here, the reaction quotient is basically saying, all right, this is lower than the K value. So if it's lower than K, nature immediately tells it, all right, you have to increase, you have to get to K. That is nature basically saying you have to increase to get to K. So if Q is low, below, so if Q is less than K, what has to happen is we need to shift. Q is going to increase until it reaches K. Well, what exactly does that ultimately mean? Well, in order for Q to increase, I need, again, products over reactants. In order for it to increase, I need to increase the amount of products and decrease the amount of reactants, which means the whole reaction is going to shift to the right. It's going to shift 2 products in order to produce more products. Does that make sense? I hope it does. Until we reach K. So if I have 100% reactants, doesn't matter what's happening, we're going to shift to the right anyway because we got to reach equilibrium. And the opposite is true if we think about Q, if we had all products. Having all products, Q, again, is equal to, let's say, 100% products over 0% reactants. So in this case, Q is, I mean, I recognize it's undefined, but Q is ultimately a giant number. It's close to infinity. It's this giant number. What that means is if Q is greater than K, then Q will decrease. In order for Q to decrease, again, Q products over reactants. In order for Q to decrease, I need products to go down, reactants to go up. That means we are going to shift to the left. We're going to shift away from products. It seems all very intense, but this is our Q, this is our K kind of idea. Again, if Q is smaller, Q is always going to increase to get to K. If Q is larger, Q is always going to decrease to get to K. So the reaction quotient as the equilibrium number at any point other than equilibrium. Everything will always go to equilibrium. And this is basically looking at what we're talking about here. So just to sum up one more time, if Q does not equal K, the reaction will shift until Q equals K. So we're going to always react. We're always going to change that. And again, if Q is equal to products over reactants, if Q has to go up, so if Q goes up, if Q needs to increase, and in fact, I'm not even going to write that. There we go. So if Q needs to increase, I need products to go up, reactants to go down. I need the numerator to increase, the denominator to decrease. Both of those will have the same effect. And that is a shift to the right. It's a shift towards products. Okay. All right, good. Because ultimately that leads us to Le Chatelier's principle. I don't know why I got to change that. Le Chatelier's principle, which is going to lead us to understanding how changes happen, all because of this idea. This idea of Q and K is the reason Le Chatelier's principle exists the way it does.